Okay, so I wanted to record a video as I promised today to discuss the stuff that we didn't quite get to in the morning, but we needed to finish up today. So, um, just to sort of recap what was we started to look at, we're looking at this phenomenon called thin film interference. And this is the notes that we'd written earlier today, so I just want to recap it. So we're talking about what's going to happen when I've got a film of a thin film in air, or does the situation is dependent on the physical thing that we're trying to create or discuss. But the first thing we want to recall is remember that I was showing in the demo with that wave simulator that when a light wave meets a boundary, then I've got two options. The wave when a wave reflects at that boundary, so now a wave can go through. So as I've shown in this diagram here, I'm just going to highlight. So here's my incident wave, this green wave. It's traveling up to a boundary. As it hits the boundary, part of the wave is going to go through and part of the wave is going to reflect. So the stuff that goes through undergoes no change to its phase information. And we'll talk about that a little bit more as we go along. But what happens is with the wave that reflects, the part of the wave that reflects, I've got two possibilities that depending on the situation, and it has to do with the relative values of the refractive indices. So if the incident wave, so if you recall from grade 10 in Snell's law, we had N1 and N2. So N1 is our incident medium, N2 is our refractive medium. And so if the incident wave traveling towards this boundary, as some of it's going to go through and some of it's going to reflect, if the incident medium is less optically dense than the refracting optical medium, then we say that N1 is less than N2. The higher the index of refraction, the higher the more optically dense it is. The reflected wave coming back is inverted in relation to the incident wave. So if I've got a crest hitting the boundary, what reflects is a trough. If I've got a trough hitting the boundary, what reflects is a crest. So this is the what we discussed this morning. So if N1 is less than N2, the wave any reflected wave comes back inverted. If N1 is greater than N2, then it comes back non-inverted, and that's the demo that we ran today. And I can't do that in this setup, so we can just remember that video, that demo that we saw today. So what I want to do, I want to consider a situation. Now this is just a situation. This is a classical thing, because this phenomenon is sort of manifested in the classic example is a soap bubble. So if you have a soap bubble, you've got a thin film of soap, and you've got air on one side and you've got air on the other side. So if in this situation we're looking at this thin film, and this is just the thin film that surrounds the bubble on all sides, I guess, if it is a true bubble. But if you ever see these wands where you dip it into the water, the soapy water, and you pull it out, you've got a big ring that's got a clear transparent film that fills the ring, and you'll see this rainbow pattern that we were talking about. That rainbow pattern is manifested because of this interference phenomenon, this thin film interference. So let's look at this situation here. So we've got a thin film of this soap in air. So I've got n is equal to 1. That's air. That's the refractive index for the incident medium, right? So this is our incident wave. I've got n is equal to 1.33, which you'll notice is the index of refraction for water, because soap is mostly water. That thin film is mostly water, so it's pretty much the same as the index of refraction for water. And I've got air on the other side of the film, and we want to see what's going to happen if I have this thickness is lambda over 4. We'll get there in a second. Okay, so the first thing we have to do, we got to look at two things, two aspects of this solution. We've got to look at one, whether I've got inversion or non-inversion upon reflection. And then two, I'm going to have a phase shift that's introduced because one of the waves travels across the film and back, the other one doesn't. So they've traveled a different distance before they come back to each other. And I need to reinforce, re-emphasize what the way I set this up this morning was, although I draw these things at angles, this is true when the light ray coming in is perpendicular to the surface. It's just that all of these rays would be on top of each other and we wouldn't be able to see them. So I only draw these with angles for the sake of clarity so that we can look at it. But it's not really the situation, okay? So we've got the incident wave. I'm going to have a reflected wave that comes off of the first boundary. Part of that wave is going to go through. It's going to refract through the film, hit the other side of the film, and come back. It's going to reflect off of the other side of the film and come back here. I'm going to get rid of these highlights. So that was just for us to see what I was talking about. So I took the liberty of drawing this ahead of time to save some time. So we want to look at this. And get my pen back. So we want to look at this and we say, okay, I have the incident wave coming back. If this incident wave reflects off of the first surface, I've got N1 is less than my N2. So this is my incident medium. This is the refracting medium. It travels to this boundary. This index of refraction is higher than this one. So if that's the case, we go back up to the note. We say that N1 is less than N2. So the wave that comes back is we say that it's inverted. So I'll just write an I to say that it's inverted. The second, the wave does refract through the boundary, hits the second side of the film, and we've got a new boundary where the N1 is 1.33. The N2 now is 1. So this index of refraction is greater than this one. That's our second case where N1 is greater than N2. It's going to come back. It's going to be non-inverted, and of course it travels across the boundary. Any transmission through a boundary doesn't affect the phase information at all. So this is going to be non-inverted. I've got an inverted wave. I've got a non-inverted wave, but this second one has traveled across this film. It's gone the thickness. So this thickness here is lambda over 4. So it's traveled lambda over 4 there. It's traveled lambda over 4 back. So it's traveled 2 times lambda over 4, which is lambda over 2. So we say that I've got this non-inverted wave has some phase shifting. We denoted this by phi when we were doing it in class. So this phi is equal to pi over 2. That's for this case because it's the thickness is lambda over 4. We're going to discuss this case where the thickness is lambda over 2. You'll see that these are our points of interest. Notice that I get this, if you remember from the double slit and single slit interference patterns or phenomena, the points of interest are when I've got a phase shift or a path length difference of lambda over 2 or a path length difference of lambda. So interesting thing happens. We've got this path length difference that's lambda over 2. So now I have to look at this. I said, well, first I had an inverted wave. So if I've got my original sine wave, if I can do this on here, and I'll draw my second wave or my first reflection is inverted from there. So so we've got this inverted wave. So that's this is my sort of first reflection. This is my incident wave, and then, but another thing's going to happen. My second reflection, I'll do this in green. My second reflection, no, let's do it in purple. My second reflection goes across it doesn't invert, so there's no inversion. It's going to have the same original phase information based on any inversions, but it's going to travel a lambda over 2. So I'm going to have this information here. It's going to travel lambda over 2 farther. So it's going to start here. It's going to travel here. It's going to have the same phase information as the other one. No, Do I have it? I don't know, I've done something silly here. So it's going to have, oh, sorry, it's going to have the same phase information as the incident wave. So it's going to start going positive like the incident wave, but it's traveling a half lambda farther. So then once it's traveling together with this first incident, the first reflected wave, now I look at the phase information. My purple wave, this is my second reflection. My second reflection is non-inverted compared to the incident wave. So it travels, it's just that it's been shifted by lambda over 2, so it's traveled lambda over 2 farther than the red wave. So now when they meet together, they've got the same phase information. So I've got two waves that have crest meeting crest, or trough meeting trough, crest meeting crest, trough meeting trough. Then we would say that this is constructive interference, so we get a maximum. So this is for the reflected wave. So for the reflected waves, relative to the incident wave, right? So the incident wave comes into the boundary. I'm considering these reflected waves. We're going to consider the transmitted waves in a second, and you'll see the interesting difference. So the reflected waves relative to the incident will have this. I'm going to have the first one, I'll be inverted. The first reflection is inverted. The second reflection is not inverted upon reflection, but it's got this phase shift of lambda over 2. And so when I combine these two together, you sort of see this as like a logical problem solving. It's a logic solution rather than any sort of real calculations. So if I look at this, I've got an inverted wave with a non-inverted wave plus this with this phase shift of lambda over 2. But when they get together, these things are actually in phase, and I get constructive interference. Right? And that constructive interference we refer to as a maximum, or I'd see a bright spot, or if depending on the type of the language of the question. Okay, now let's take a look at. So this is for the for the reflected waves. Okay, let's look at the transmitted waves. So I'm just going to set this up for the transmitted waves. So for transmitted waves, again, relative to the incident, I'm not going to rewrite that to save some time. We've got, we have to look at this first. The first one, the purple one, it just travels right through. So there's no phase change, or sorry, that shouldn't be inverted. It should be non-inverted. There's no phase change because when it goes through, right? When it passes through, I only see phase changes upon reflection. So let's take a look at this. I go from, so the wave travels through. It hits the second side of this film. It reflects. We already said that reflection is non-inverted, because we've got an index of refraction of 1.33 going into an index of refraction of 1. The reflection comes back non-inverted. Likewise, when it hits the other side of the boundary, it's going from 1.33 into 1. So I again get no inversion. So I get a non-inverted wave, but it's got a phase shift. Okay? Now, the things relative to the first one, they both traveled across. Both the purple wave and the red wave have traveled across it once, but the red wave has gone back back to the beginning and back to the first side, and then back again to the second side. So it's traveled again two thicknesses. It's gone a thickness back and a thickness forward again, and it meets up with the wave that transmitted through. So this phase shift is also lambda over 2. Okay, but now, so we've got these two non-inverted waves, so they have the same phase relationship, but then I shift that wave back. Okay, I have to, at this point, I'm looking at the time here, there's a 15-minute limit to the video on YouTube, so I'm hitting that 15-minute mark. I'm going to put part 2 up in a few minutes.